Okay, now we could start by plugging in points. Go in increments of pi over 2. Or even pi over 4. But what we should totally understand at the very outset is that in the XY plane, this is just a unit circle. And I said t from 0 to 4. I meant t from 0 to 4 pi. Okay, if I could do t from 0 to 4, we would get all the way around the circle. But now, the thing I want to focus on is that we go into the first quadrant, into the XY plane, and we see exactly what we have. Okay, now we have some z's, which means that these points are not going to stay in the XY plane, but we know what the X and Y coordinates are going to be. They're going to be on the circle. And got the points where X equals 1 or -1, Y equals 1 or -1. This is just a conic section. And of course, this is where we have to understand parameterization. You come in without a good foundation in parameterization, it's going to be much more difficult. And all we've done is we've parameterized the unit circle, which is one of the most fundamental parameterizations. We really might think about reviewing parameterization. Okay, there's a badly drawn unit circle. And of course, you're going to go around the unit circle once as t goes from 0 to 2 pi. So we go around the unit circle, and then we go around it again because t gets to go all the way up to 4 pi. So we make 2 circuits of the unit circle. So t equals 0 here. Also t equals 2 pi, puts us at this point. Equals pi over 2 or 5 pi over 2, puts us here. Equals pi or 3 pi, which is here. Equals 3 pi over 2 or 7 pi over 2, which is here. So it's helpful if the first thing you understand is what the shape of this thing is in one of the coordinate planes, just like when you're doing a quadratic surface, you look at what it does in each coordinate plane and you get a picture of what the quadratic surface is. Here, whichever plane gives you the best picture. Now we could actually do 2 planes. We could do like the X plane and the Z plane, or the XZ plane, sorry, 2 axes on the XZ plane. And we'd essentially get a graph of the cosine function. That would actually be the, let's just move on to what we might actually want to do, though. No, let's look at that. Okay. So we've already got a good bit of the picture of our graph. If we draw a unit square, I'm not actually going to draw the square and everything up, but it's not a bad idea to draw it. And we've got the unit circle in the XY plane. Then ask ourselves, what happens to Z? Well, looks like Z increases. Linearly. From 0 to 2. As t goes from 0 to 4 pi. If t is 0, obviously you get 0. T is 4 pi. Obviously Z is 2. I mean, t is, I think I said it right. T is 4 pi, then Z is going to be 2. And so, well, if this is 1, then let's see, we'll put 1, 2 up here. Now, how do we locate points? Well, I don't want to label the one, but we understand that that's it. Okay. First of all, we start at this point. At t equals 0. Because that corresponds to this point. We're going to be back at this point when t equals 2 pi, but we're going to be 1 unit high, aren't we? And if t equals 2 pi, we have, we're back to this point on our unit circle, but z equals 2 pi over 2 pi, which is 1. So somehow we're going to get from here to a height of 1. Well, 1 is about that, so it's going to be a point above here. So after we've gone through the whole circle, we're going to climb up to here. And then, that point projects from here. And then there'll be another point where these two lines intersect. And that's where we're going to be after t equals 2. Okay. With that much knowledge, since we're climbing linearly, we're going up a staircase, spiral staircase, sort of. Actually, helical. But, not really a spiral, but a spiral doesn't get bigger or smaller. There's probably a name for what that is. Current events over here. In 1982, that was like yesterday. Okay. Okay, so what do? Well, we can do a point above here, we do a point above here, a point above here. Actually, we do 2 points. Okay. We round to here, t is pi over 2. So that z would be 1/4. So we go up z equals 1/4, we get a point like this. Okay. Now, I'm not labeling it all because this should be something with this much guidance you can label and try to do a really nice job of. Okay, and then after we go another 2 pi, well, t will be 1 unit greater than it was. We go another 2 pi. Every time we go 2 pi, I'm saying t when I mean z. Every time we go 2 pi, z increases by 1, doesn't it? Kind of want to have that concept. 1 is like this, so that's going to put us up about here. So we go around, we go through this point, we'll go through another point here and another point here, and then we'll curl around to here, and then we'll go up and we go up a little higher here, and so forth. Okay. And then we can fill in, where are we here? Well, this is t equals pi over 3 pi, which means that z will equal 1 or, sorry, z will equal 1/2 or 3/2. Well, half would be half of this, and we'll go up about this high. And then we go up another unit. And then we do the same thing over here. We're going to be up at 3/4 of a unit now, pretty close to 1 unit. And then 1 unit higher after another 2 pi. So now we can kind of draw a picture This one should have really been a little higher. But actually, I'm gonna make it a little bit higher than here and maybe. Okay, so now I just kind of pledge a curve in here. That's not too awful bad. Better than I usually do. Okay. Now Caleb, I'm gonna turn on a chat box. So if you have a question, you're welcome to chime in. And I better stop calling you by name because this is a video. Okay. Oh, you out there, but you know who I'm talking about. Okay. So if I'm recording, I better not use your name. But if you have a question, you can type it into chat. Or you can make some sort of noise that doesn't identify you. But I'll kind of keep an eye on the chat. And if I see something come in here, I'll stop. And if you have a question, we can answer it. Okay. So continuing on. There we have it. That's just a little preview. I want to know how fast we're going at a given point. And just take the derivative of each of these and use the Pythagorean theorem. Because the derivative of this tells me how fast I'm going in the x direction. The derivative of this tells me how fast I'm going in the y direction. And the derivative of this tells me how fast I'm going in the z direction. Now that's always 1 over 2 pi. Okay. So if I know my 3 components of velocity, I can find the magnitude of velocity. Dot the velocity with itself. Do that. Or use a Pythagorean theorem, which comes out to the same thing. Okay. Of course, if I dot the velocity with itself, I better take the square root. So now I can say that this curve is defined by an R vector. What color am I looking for? I'm not finding it, whatever it is. What is this? Okay, so I have an R vector. Let's just say if the R vector goes out to this point on the curve. And let's make the curve a little more prominent. So now the R vector doesn't contrast with the curve. Okay, I'm going to make a blue R vector. This is the vector R of pi over 2. Which is multiple of I plus multiple of J plus a multiple of K. Okay. Can you fill that in? What's multiple of I? What's multiple of J? What's the I, the J, and the K? In that vector that I just drew there. I'm going to pause the video. If I can find the button to pause the video, and I can't because the chat is up there. And the one thing that I need is the button for the recording. And it's not letting me find it. This didn't used to be the case. I did this for a year from home. Didn't happen. I couldn't even find the chat button now. Good heavens, I might be stuck. Now I've got nothing. Come on, Zoom. Can't do that. No, I'm trying to close the chat. Well, this is something. There should be a button over here for chat, but there isn't. There should be a button to stop the recording, but there isn't. Okay, I'm going to risk this. No, I've got nothing. Okay. That wasn't the thing to do. Okay, so what we've got is 0i, because of course, you know, we're above this point here, which is right above the y-axis. And then we have plus 1/4 j, that's 1j. 1/4. And I'll write that in the middle, 51 wire, and then plus 1/4 k. All right. Okay, well, what's the vector r of t? The vector that stays rooted at the origin and keeps its tip on this curve. So for example, then r of I would be -1, 0, 1/2, right? Okay. But what's r of t? What's a general function? It tells us where the tip of that vector is at time t. Okay, so r of t pretty obviously equals, well, I can write that it's almost by definition, x of t times I plus y of t times j plus z of t times k. You don't have to write that out. I mean, if you just wrote out what it is, which everybody did, that's good. But that's in general what it'll be. If you know how to parameterize in terms of x, y, and z, then you know your r vector. And so your r vector is this, and that equals cosine ti plus sine tj plus (2/2 pi k). Okay, so my next question is, kind of a spiraling coil, it's a helix. What if I want to stretch it out this way? What would I change? Okay, so, you know, the response I got was you could decrease the denominator, which would increase the coefficient of t, or you could multiply the numerator by some number greater than 1, right? And which would accomplish exactly the same thing. Okay, so you probably wouldn't do both. Probably just multiply the numerator. What if I multiply the numerator by 2 pi? Well, then you go up to 4 pi up here, not just 4. Go 3 times, you know, a little over 3 times as high. That's pretty easy, okay? Okay. What if my staircase won't quite fit into this? Let's say this is a meter and this is a meter. So my units are a meter. So what I want to do is I want to compress it this way. Okay. So I want to compress it along the x-axis. let's say without changing it along the y-axis. Because I want to make it use of my space. I don't want it to get too steep. Okay. I'm climbing up 2 meters, which is about what you do to climb. Short. Floor above. So what do I do to compress this thing in the X direction? Okay, so we just multiply the X by a number. Let's say we just want to shrink it about 10%. Multiply that by about 0.9. Actually, want to shrink it 10% would be 0.91. But and that would accomplish it. Of course, that would make my shape down here an ellipse, wouldn't it? So that would compress it a little bit. Okay. So I could do an elliptical helix. Not sure that fits the definition of the helix, but with the adjective, a helix modified to elliptical projection. Anyhow, there it is. Okay, now, what if I wanted to get steeper and steeper as I go? Let's say this is an amusement park thing, and we want to see how high somebody can climb before they fall off and get injured. Okay. Or before they start sliding back down. Kind of a grease pole type challenge. Okay. So what would we change if we want to make it get steeper and steeper and steeper? Okay, so we had a good response, which was if you want to get steeper and steeper, make that a t-squared. Okay. But you know, the graph of t-squared goes like that. So you think of, you have a t-squared path, now you wrap it. Okay. In a particular way. If it was t-squared, you'd be here after one, but you'd be a lot lower here and lower here and lower over here. Because you'd be steep and steep. If you square 1/4, you get 1/16. So you'll only be up 1/16 of the unit here, down a fourth of the unit here, and 9/16 of the unit here. Okay. So you'd only be up to 1 unit here, but you'd get there with a path that goes steeper and steeper. And then between here and here, you go all the way up to 4 units high. You go all the way up to here. So the thing would get pretty skinny as you go through another cycle. Okay. We could make it e to the t, an exponential, which gets, that stays pretty shallow for a long while. Actually, it starts with a slope. If you start at 0, right? Start with a slope of 1, and then just goes nuts. So that by the time you're out to t equal 2, you'd have e squared over 2 pi, which would be something over 7 units high. And after 1 unit, you'd be up all the way to e, which would be like 2.7. You'd be all the way up here, maybe go way up. Okay, well, you understand how that works. Now you understand that if you think of your position as a function of t, which you have, there's your function. And the derivative of this function gives you your velocity. And the derivative here is pretty straightforward. As a matter of fact, you find that the derivative of this would be a sine, the derivative of this would be a cosine, and of course, the cosine would be negative. So the sine would be negative, there you have a cosine. Then you just have 1 over 2 pi here to be constant. Okay. So if the square of this plus the square of this, when you take the derivative, would still be 1. Still have a sine and a cosine. The sine would be negative, but you're squaring it. And this would still be the same. So that if t is your time, your R vector would move in such a way that your speed along the curve would be constant. And your velocity would always be tangent to the curve as it needs to be in any case. Okay, and you have an acceleration. You take a second derivative, this on the first derivative, the k component will become 0. But these would still be just sines and cosines. You'd have a negative sine, a negative cosine plus a negative cosine I and a negative sine of j. But when you square those, you get the same magnitude, which would still be 1. But they're negative, so they're pointing back toward the center, so it's kind of centrifugal. But not exactly because of something, okay? Actually, it would be centrifugal, it'd always be toward the axis. You'd never have an acceleration component in the vertical direction because the vertical motion is at constant speed, constant velocity. Okay, now if you did a t squared there, that changes everything. Because then your velocity function would have a t dependence and your acceleration function would be constant in that direction, but you'd have like a constant force pushing you up. We'd also be accelerating along the curve. Well, that's what we do for the assignment after the one. We'll learn how to deal with space curves. Okay, so this is a good example of a space curve, but there are many other examples. But just to think ahead a little bit. Let's say we want to get cruel with our velocities. Okay, we're going to send somebody along this curve, which would be fairly gentle. For this, constant acceleration of like a meter per second squared. Kind of what you have if you start out at the stoplight, doing moderate acceleration. And for any of the boards that are viewing this out there across the world, if you don't understand the physics, that's okay. All right, using the physics, that's what I'm using. I have some background. Okay, so anyhow. Okay, there's your R2 vector, right? What's V of t and what's A of t? Velocity, acceleration. Well, V of t is R prime of t and A of t is V prime of t. So we're just going to do a couple of derivatives. So if you can do those derivatives, and let's see what we got. Okay, so derivative cosine of t squared is negative 2t sine of t squared. Derivative of sine of t squared is 2t cosine t squared, and that's times j. Then you're going to have 2t k. Straightforward application of the sine rule. Derivative of the inner function times derivative of the outer function, but the inner function doesn't change. However you understand it, make sure we've got that. Then A of t is v prime of t. Okay, well, now you've got a product rule. You got the two t function and the sine of t squared function. Well, again, I'm not going to go through the details of the calculus. You just have to know and review that if necessary. But you're going to get first of all minus 2 sine t squared when you take the derivative of the t. That's kind of sine of t squared. That's like your f prime g. And then your f g prime or your g prime. Your g is the sine of t squared now. And the derivative of that is again 2t times the cosine of t squared. With the 2t you get from taking the derivative of the sine of t squared multiplies this negative 2t, giving you negative 4t squared. Now, does that agree with what you got? Okay. So you look at closely at what you got. I'll just look to make sure you were using the product rule and the chain rule. Okay, then. Very similar. When the j as derivative of the t is 1, so you get a 2 cosine t squared. And the derivative of cosine t squared has a 2t in it and goes to the sine with a negative. And if you does that agree? Right? And do bonehead things. See it all the time. And then 2k. All right. Okay, so what's the magnitude of the velocity? And what's the magnitude of the acceleration? Gets messy. And then what's a unit vector in the direction of the velocity? And I want to ask you for a unit vector in the direction of the acceleration. Okay, so the magnitude of V, you just take the square of this, the square of this, the square of this. Pythagorean theorem, put it over the square root. This is going to give you 4t squared sine squared of t squared. Four t squared and cosine squared of t squared. 4t squared. Well, first thing I would notice about this is it all has a everything has a coefficient of 4t squared. And if you factor 4t squared out, you got that sine squared t plus cosine squared t plus 1. Now you might pick up on the fact that you got same quantity times the sine squared of t squared and times the cosine squared of t squared, which should immediately invoke the Pythagorean identity. So you might see that, well, that's just going to be 4t squared times 1. So you got 4t squared plus 4t squared, and then you could factor out the 4t squared. Or you could see it as 8t squared, and then see that 4t squared comes out of that, which is perfect square. Anyhow. And without writing out the fact that sine squared t squared plus cosine squared of t squared and sine squared t squared, or some sort of t squared, it's a sine squared and the cosine squared of the same argument always add up to 1. You got 1 plus 1 here. You got 2t times the square root of 2. Now, what does this tell you about the speed of the thing? Well, first place, you always get positive, but speed has to be positive. We're doing a magnitude, so it better come out positive, right? So that doesn't really tell you anything about what direction it's moving in. Okay, if we have, we started with negative cosine squared and negative sine squared, we'd be moving in a different direction on a different helix. Okay, we'd still have the same magnitude of velocity. You can check that out. So my point is, but this doesn't tell you what direction you're moving. It just tells you how fast, you know, the direction comes out of the vector when you do a unit vector. And we haven't done that yet. There it is. And it's telling you that you're speeding up at a constant rate. So you sort of have a constant acceleration, except not really, because your direction in space keeps changing. So you don't have a constant acceleration, you have an acceleration of constant magnitude. Yeah, well, that's good. Then we'll do the V over magnitude of V here, and that one is here, and V over magnitude of V. I'll do with that, we'll go up here. So V over magnitude of V equals all this. Of course, we have 2t as a factor, right? I don't have a lot of room to write. I better go up a little higher. Don't need room for 5. Think about how I could compress this thing, how I could compress this thing. Okay, I'm going to take the liberty of factoring out of 2t my velocity. Right. And then that's over the magnitude of my velocity. It's a lot easier to write 2t square root of 2 than it is to write out this whole expression. And when you do, of course, you see that the 2t divides out. And now you know that the magnitude of the numerator will be the square of this plus the square of this plus the square of this with the square root. But the square of this plus the square of this is 1. And this is 1, right? So I have square root of 2 in the numerator, square root of 2 divided by square root of 2. Going to do the magnitude of this is 1. And it had better be, because this is supposed to be a unit vector. So you kind of want to see that, you know, kind of check yourself. One thing it's nice to think of. Okay. So this would go there, set it up, put it all the way up here. Well, now you can do the magnitude of your A vector. It's going to be a mess. But you are going to have common factor of 2 in all these, so it might be a good idea to just factor that out at the beginning. But there's not a whole lot more you can factor out. I mean, once you factor 2 out of your K component, you've done factoring. Okay. So it gets to be a mess. But very easy to do A dot your unit tangent vector, okay? So kind of quickly do that one for me. Something I want to illustrate there. Okay. To do this dot product, and y'all are working it out, and I assume, everybody else across the world is working it out. You're gonna multiply the I component of your A vector by the I component of this vector, which will give you all this times the sine squared of t. So. Not probably don't have time to write it here. I should probably actually do the sensible thing. Even though that kind of goes against those three. So. First term is going to have this component times the sine squared of t and there'll be a square root of 2. Well, I can say that right there. Sine t squared times all that is going to give me you're going to get negative 2 sine squared of t squared minus 4 t squared sine squared of t squared. Not sine squared, sine of t squared, cosine t squared. Okay. And that'll all be over the square root of 2. Then it's going to be cosine t squared times this term, so it's going to be a negative 2 cosine squared t squared minus 4 t squared sine t squared cosine t squared, all that over the square root of 2. You got it right yet? I mean, so far? I think it's all right. Okay, then it's just k out of the 2k with the square root of 2. Okay. Now, in these terms, and what am I looking for? I'm looking for sine squared plus cosine squared. Okay. I mean, I've got a sine squared of t squared, I've got a cosine squared of t squared. Okay, so these two are going to go together to give me a negative 2. Well, from this and this, I get this. From this and this, I mean, I'm getting a sine of t squared times a cosine of t squared twice, right? Well, better give me. It'll give me an 8 t squared times a sine of t squared cosine t squared. Well, that's minus 2, and that's plus 2, right? Looks like those two go away. That's just 1, so that's minus 2. That's plus 2. And I get negative 8 t squared sine t squared cosine t squared. Over the square root of 2. And there's more I can do with the sine t squared, cosine t squared, but I don't want to go too far. So it can get messy, but a lot of times, a lot of stuff simplifies. So this is a whole lot simpler than what it looked like it was going to be. If I then subtract this. Well, here's a picture. Let's play it this way. Okay, so here's we usually call that T, capital T for unit tangent vector. Okay. So here it is. And we have our acceleration vector, which maybe come out like this. Of course, this is all 3 dimensions. I'm not trying to depict it accurately. Right? When I dot a vector with a unit vector, I get its projection. And its projection I do this vector. Try to write v over negative v over cos t. Right. Its projection onto the vector t of your acceleration vector. And I call that a parallel. It's a component of a parallel to your direction of motion. Okay, personal story. Passenger side door on one of my vehicles was loose. I went around a curve and it slipped out and got stuck in traffic. Well, it wasn't that much traffic. I got off in 100 yards, called AAA. They came out and said, hey, we can't even tow that thing's too wide. It's not legal. Well, I don't know if you ever looked inside of my vehicle, but you know that anything you want is in that vehicle. You want a hippopotamus, there's going to be one in it. I haven't seen it in years, but I know there's one in there. Okay. So he looked and said, hey, is that a hammer? I said, yeah, here's the hammer. I pulled it out of the junk and handed it to him. Okay. It's right on the passenger side. You know, you got to have a hammer. Last time I used a hammer was in that vehicle. I left it in there. It's a new one. He said, no, if I just had a 2x4, went back to the rack on the back, picked up a 2x4 and handed it to him. They took it and he beat on the thing until the door would close again. At that point, it's perfectly drivable. I just make sure the door stayed closed and drove it down to having an auto lube and say, hey, tell me, can you get a hinge? Can you fix this? Turns out, you know, for about $600, yeah, they could. I said, wait a minute. That door closes if I push it forward and up a little bit. Okay. For $600, I'll deal with that. Okay. And it turns out that it's actually, I got another problem. It's an old 2000. It's basically a Cadillac. It's actually an Oldsmobile, but it's the same build as a Cadillac. So it's a really well built vehicle. It's running great. So I'll keep driving until it dies. Didn't pay much for it, didn't put much into it. When it dies, give it a nice little funeral. Let it go. Okay, so anyhow, every morning when I drive up here, and every time I drive it, in order to get the door to close, because the panel over here is loose and I can't really pull it shut. So I got to put my finger between the window and the molding here and pull it shut. Well, my fingers slip off eventually, and I'm limited to how hard I can pull without tearing the tips of my fingers off. So I always make a curve, like, go around a curve like this. Okay. When I go around the curve, of course, the triple force helps me, and I pull the door shut, and it latches nicely. Okay. Well, that's a direct application of this. Okay. When I start out, I accelerate forward, which tends to make the door kind of go backward a little bit, or seem to go backward, because the door just keeps wanting to stay still. And you can do that. But I also make a sharp turn to get the centripetal force. So I'm turning and I've got an acceleration vector, some of which is going forward, some is going in this direction. And I've been working to optimize. It takes a little coordination. It took me about a year to figure out how to do it. No, it takes a little coordination. So I've worked out the balance between the parallel and perpendicular components of the acceleration vector, because it's a perpendicular component that gives me centripetal acceleration. And that's actually for most of the force, the apparent force that I feel in that non-inertial change of reference in my vehicle at that moment allows me to close it. So this is directly relevant to how to save $600 if you're ever in that position. And of course, I can work this stuff out. I didn't actually work it out conceptually. I understood what was going on. It's the first time I did it. And I almost took the fence of the house up, and I managed to get back on the road and weave it. Wasn't like that. Figuring out how to optimize that, though, is what I need to feel at a given instant to optimize this. I can work it out mathematically, but what's it feel like? What I need to be doing with the accelerator, what I need to be doing with the steering wheel, and when should I pull? Pretty interesting problem. Don't go out and practice it. If there's any obstacle like with the traffic, if you ever want to play around with that idea, go out to an empty parking lot, and there's nothing to do. Play around with it. It's an interesting exercise. Okay, well, digression aside, okay, so what we have is this. What I really want is the perpendicular component of this acceleration. So there's a perpendicular component. This speeds you up. This creates centripetal force. Okay. These are perpendicular. This vector plus this vector equals this vector. Well, if A parallel plus A perpendicular equals A, then A perpendicular is A minus A parallel. It's easy to calculate A parallel. That's easy, it's easy. Okay. We just calculated the magnitude of A parallel. Of course, I have to multiply it by the unit vector V over V. Got to multiply by this unit vector to get a vector. But right now it's just a number. Or more compact A dot T times your T vector, unit vector. Okay. Well, we're only a minute over time, so I got to talk for a while. Okay, quickly. Your assignment is on space curves. Okay, this thing that we did with helix and stuff and how you modify it stuff should give you a context for that. There's a couple of problems that, I didn't go over because I think you'll get them, especially if you understand parameterization. If you come in here and don't really understand it, that's what we'll talk about, because we've already talked about most of the next sections. Okay. But I don't think I need to talk about those things. I think you'll get them. If I'm wrong, and I might well be, tell me about it so we talk about it, right? Because I'll kind of probe a little bit to see what you understand. And there's a lot of stuff about limits and domains. That's just calculus 1 stuff that you might have to review limits and domains a little bit. And again, if you have problems with it, we'll talk about it. And if you have a lot of problems with the assignment, I'll probably give you a little bit of an extension, but try to get by it without the extension, because the next thing we need to talk about is curvature, and we have to talk about how to partition intervals and set up intervals. And that's always a big challenge. So the third section, which will be due before a week from today, is going to be kind of a challenge. And it's going to set the tone for being able to set up intervals for the rest of the course. Okay, which is why I jumped ahead and did this partly because it's just kind of really neat anyway. So kind of, well, that's where we are. We'll see where we are next class. We'll see how much we got to talk about which. Okay, we do have to talk about curvature and R planes. Okay.